welcome all of you on behalf of the organizer who were just named, Malcolm Brown, Toshi Sunada, and Peter Kuchman, who unfortunately from family reasons cannot be today with us. We had a great time 3 years ago, great half a year, and we hope that the workshop will be at least as good. So let me now introduce the first speaker, who is Brian Davis of King's College, and his title is Weyl and Non-Weyl Resonances on Graphs.
The most important thing is that I have to turn my microphone
on.
So of course this will.
This is now done. I'm very pleased to be able to speak here again. I think of the Isaac Newton Institute as being the mathematical version of heaven. It's such a wonderful break from the environment one has to endure in universities, and we can talk about the things we really love. Before I start, I would like to apologize for making an advertisement for a new journal of spectral theory, of which I have been persuaded to become the editor-in-chief, but it was actually really the idea of Ari Laptev over there. He had the vision and saw the need for such a journal. I'm not going to give you huge amounts of information. I mean, if you have Google, you can easily find out about it either by typing in Journal of Spectral Theory or typing in European Mathematical Society. So I'd just like to encourage all of you to think about the possibility of submitting articles to this journal, which I must say has a wonderful board of editors, including Ari. I seem to have gone. Well, this is very odd. Anyway, let me start off by saying that this is what I'm going to be talking about is joint work with Sasha Pushnitsky, which had been in some way inspired by an earlier paper of Pavel Exner, though it's not altogether obvious that this was the case. After the work was done, I then got into collaboration with Pavel and also with an associate of his, Yuri Lipovsky, in Prague. And I will not be talking principally about the extension of this work, a very big extension of this work, which Pavel proposed, but with the original work with Sasha Pushnitsky, which should have been here on the next slide. That's why I paused, because it seems as if I've not quite loaded the final version. Anyway, so I'm going to be talking about graphs, and I'm going to be talking about resonances of graphs. And although all of you know probably more than I do about graphs themselves, perhaps I ought to say a few words about resonances, because not everyone is bound to be very familiar with them. We're talking about a self-adjoint operator, a typical Laplacian on a graph with typical boundary conditions at the vertices, but I will say more about that later. And we're talking about complex eigenvalues. Now, you all know that a self-adjoint operator can only have real eigenvalues, and so perhaps I ought to explain what resonances are. They're of great interest to physicists because the real part of these eigenvalues is supposedly the energy of some entity, and the imaginary part is closely related to the decay rate of that entity. So there's very real physical significance in these things, even though there is a theorem, which I'm not going to contradict, that self-adjoint operators can only have real eigenvalues. So the question is, what do you mean by a resonance? We're talking about a solution of the equation, which if you're on a manifold, you could call it the Laplace-Beltrami operator. If you were on the real line with a Schrödinger operator, you could be just looking at the equation at the bottom of this screen. The difference between this and eigenvalues is that k squared is not required to be real, and therefore the solution, which you can think of as being a classical solution of the differential equation, is not in the L2 space. Now, of course, if you simply say it's not in the L2 space, then you can choose k arbitrarily, certainly in the case of the Schrödinger operator in one dimension, for any k, complex or real, there are always two independent solutions of this. So one has to put on some extra condition which singles out some special k's for which the solution has special properties. So that's, I will say more about this in a moment, but let me next go on to the graphs. The kind of graph I'm talking about is what I think is unfortunately called a quantum graph. I'd much prefer to call it a continuous graph, but we're thinking of a set of intervals, each some of finite length with two ends, and some of which are semi-infinite intervals. Whenever I talk about a semi-infinite interval, I will call it a lead, and I will show it on the diagram by having a little arrow on the end to indicate it goes off to infinity. So on each of these edges, each of which has a different length, and you specify the length, you're looking at the operator minus d squared by dx squared, and at the vertices you have a boundary condition, and there are many different boundary conditions, and the later paper that I wrote with Pavel Exner and Yuri Lipovsky investigated the same sort of questions as I'm going to be talking about under much more general boundary conditions at the vertices, but here I will restrict myself to the most simple of these, which by some people are called Kirchhoff boundary conditions, which Pavel doesn't like. By other people are called Neumann boundary conditions, which possibly you would like even less. But you like to call them free boundary conditions. Anyway, I will write down what they are in a moment. So we have an operator of this kind. I am calling it Kirchhoff boundary conditions. Now what I am going to do, I'm going to require that on each interval you solve the differential equation minus f double dash equals k squared f for some complex k. That you require that as you approach any particular vertex from different edges or leads, you get the same value, so that the function is sort of naturally fits together to be a continuous function on the whole graph. And you also require that if you take any particular vertex and you calculate the first derivative at that vertex in the outward direction from the vertex along all the different possible things and add them together, then you get 0. In particular, if you had a vertex which just had two edges coming out of it, one to the left and one to the right, then that vertex disappears under these boundary conditions. The function is continuous, and the two outward derivatives have sum 0, so the two derivatives, if you calculate it in the normal way to the right, are equal. So any vertex which has just two edges or leads going into it, under this Kirchhoff boundary condition, can just be eliminated. And conversely, if you like to put in an extra vertex or two for reasons of computational convenience, then it makes no difference to the spectral theory or the resonance theory. Okay, now the merit of the Kirchhoff boundary conditions is that you can transfer from the operator to the quadratic form. And I'm now here thinking of functions which are in L2, and the quadratic form of the operator is given by this equation. When you do the integration by parts, because you've got Kirchhoff boundary conditions, the things all work out exactly as you would like. And because of this quadratic form, you see HFF is greater than or equal to 0. That means that the spectrum of the operator is non-negative when thought of in usual Hilbert space terms. And in fact, it's well known in this sort of context that the spectrum is not only non-negative, but it's the whole of the interval from 0 to infinity. I mean, you can look at this from many different points of view, but if you go far enough away on one of these semi-infinite leads, then for any function which is far enough away, it can't see the rest of the universe. It only is aware of what's around it, and so by an approximation argument you can do that, or alternatively by a scattering argument. Relative trace class perturbation theory tells you that the absolutely continuous spectrum is the whole of the interval from 0 to infinity. The interesting thing about graphs of this type is that you can have bound states embedded in the continuous spectrum. Now, those people who are familiar with Schrödinger operators in one or more dimensions know that under very weak conditions this is impossible, but in waveguides and also in graphs it's actually very easy. And let me try to explain why this can happen. I'm sorry, this is an expert audience of graphs, and you probably all know perfectly well why it can happen, but there may be one or two people who would like to me to explain it. Suppose you've got a graph with a closed loop here, which the edges of this closed loop are all mutually rational in length. And in this particular case, I've taken the simplest possibility of a 3, 4, 5 triangle. Now, you don't need to know anything about the graph at all, apart from the existence of a closed triangle or another closed loop whose lengths are all mutually rational. Then you can put a function on this graph which is 0 outside the triangle, and because of the continuity condition, therefore also has to be 0 at the vertices of the triangle itself. And I've shown a suitable eigenfunction here, where if the curve is outside the triangle, the function is positive, and if it's inside the triangle, then it's negative. And what you notice here is that at, say, this vertex, it approaches the vertex being positive, and it goes away from the vertex being negative, and that means that if you look at the two outward-going derivatives, the sum is equal to 0. And of course, I'm lucky that I can do it, because if you change sign at every vertex, you may or may not get back to the right sign. But you can do it. And not only can you do it, but every such closed loop whose edges are mutually rational generates an infinite set of eigenvalues, L2 eigenvalues, whose energies get higher and higher. Now, generally, of course, a graph does not have mutually rational closed loops, and generally it doesn't therefore have any bound states, but it can happen, and when we are talking about resonances, you have to include the possibility of these bound states in the way that you're counting them. In fact, from the point of view of this lecture, I will regard a positive energy L2 eigenvalue as being a resonance. So we include the resonances as the positive energy eigenvalues as special kinds of resonances. And there's plenty of justification for that, as you will see right at the end of the lecture. Okay, so we're looking for a solution of the equation on each edge, satisfying the big kickoff boundary conditions, and also what I'm going to call an outgoing wave condition, which is that when you look at the semi-infinite leads, the function actually is of this particular form, f of 0 times e to the ikx, so there are no terms or 0 coefficient corresponding to e to the minus ikx. Now, I've actually said here that the imaginary part of k should be less than or equal to 0. I need not have specified that because if the imaginary part of k were positive, then looking at this final thing, you would deduce that the eigenfunction or solution decayed exponentially fast as you went off to infinity. That would mean it would be an L2. That would mean that k squared was actually an eigenvalue of the operator. Now, if k has got a positive imaginary part, the only way that k squared could be real would be if it was negative, and we already know that the operator is positive. So this equation cannot have any solutions with the imaginary part greater than 0. As far as the imaginary part equals 0, it is not absolutely obvious that, I mean, of course, if the imaginary part is 0, then k is real and k squared is real. And so one might say, well, obviously this must be an eigenvalue. It's not quite so obvious, because all you know, if k is real, is that the solution on each lead is oscillatory and bounded. You don't know that it decays exponentially. And so it can only be an L2 eigenvalue if the function actually vanishes at the beginning of every lead. But it can be proved that that actually does happen. That if you have a solution of this type with k real, then at the beginning of every lead the function vanishes, and you actually have an L2 eigenfunction of compact support. This is one of many things that one has to check. And one of the others is that I have used the classical definition of resonance. There are 4 different definitions of resonance, and there is some work needed to establish that they are equivalent to each other. Here is one of the other definitions, which uses what is called exterior complex scaling. And once again, this is not something that everyone knows what it is, so let me try to just explain it in this particular case, which is rather simple. You take the original operator, which is minus d squared by dx squared on each edge and each lead, and then you look at the leads, that is the semi-infinite intervals, and you multiply the operator minus d squared by the x squared on that lead by e to the minus I theta over 2, the same complex number on every infinite lead. Now, that has a dramatic effect on the spectrum, because the continuous spectrum of the operator is not affected by what happens in the finite part of the graph. It's only affected by what happens in the semi-infinite leads. And since you've rotated the operator by this e to the minus I theta over 2, should it be e to the minus I theta over 2, e to the minus I theta? I can never remember. Anyway, it rotates the continuous spectrum. So here on this line is the continuous spectrum rotated through the suitable angle. What actually happens is that you now have a new operator which is not unitarily equivalent to the old one. Well, of course, its spectrum is continuous spectrum is totally different. But this new operator does have eigenvalues in the lower half plane. And these eigenvalues do not depend on the angle theta. As theta increases, you uncover more and more eigenvalues of this operator. But once the eigenvalue has been uncovered, it doesn't depend on theta. If you take theta round all the way to pi, then you have revealed all of the complex resonances below the complex plane. And I've also, as you can see, shown the possibility of certain resonances on the positive real axis, that is, eigenvalues with compact support. So that's the complex scaling approach. You look at an operator which is not unitarily equivalent, which is nevertheless has the same positive real eigenvalues as the original operator, and has resonances which do not depend on theta and which coincide with the definition I just gave. And the third definition of resonance is you look at the analytic continuation of the green function or resolvent kernel of the operator, and the fourth definition is by looking at the analytic continuation of the scattering matrix of the operator. But I'm going to confine attention to the definition I just gave, which is the simplest and most concrete one and best adapted to doing the calculations. In the paper with Sasha Pushnitsky, a lot of work was put into actually showing that certain things which seem more or less obvious are actually true. That is, certain different ways of defining the same thing, very different ways of defining the same thing, give the same answers. Okay, so now I want to actually start talking about eigenvalues and counting functions. Let's suppose we go back to the situation where there are no leads. In that case, the graph Laplacian subject to these Kirchhoff boundary conditions has discrete spectrum, and there is a standard formula for looking at the counting function. That is the number of eigenvalues less than equal to some number. Now, I'm going to be getting into some difficulties because some of the formulae that I write down differ by a factor of 2 from what you are familiar with. And I'm not sure I want to explain this, but it's one of it's more convenient to use a Weyl formula which is a factor of 2 different from the usual Weyl formula. It depends on whether you take k to be greater than or equal to 0, as I have up there, or you just take k to be real. I mean, if you have k real, you could look for every k there's a minus k, so every eigenvalue in some sense has 2 copies if you parameterize by k, although there's only one eigenfunction there and only one eigenvalue lambda. So this is the Weyl formula, which says that if you parameterize by k, the number of eigenvalues less than or equal to r grows linearly with r, and the constant is Weyl's constant, which is the volume of the finite part of this graph. Now, what one expects normally is that when you add on this infinite number of leads, the finite number of infinite leads, then the eigenvalues typically disappear and they turn into resonances. But since each eigenvalue should turn into a resonance, you might hope that the resonances would have the same counting asymptotics as the eigenvalues of the finite graph had. And so that is the natural conjecture, and there are a number of contexts in which that has been proved to be true. In particular, it's true for Schrödinger operators in one dimension, in which you have a potential of compact support. The relevant, what we might call volume, in this context is the length of the shortest interval containing the support. So it's the difference between the maximum point on the support of the potential and the minimum point on the support of the potential. It doesn't matter how rapidly the potential decreases as it approaches the two ends of its support, the Weyl asymptotics still holds with that length as being the effective volume. So the question is, can one prove a Weyl law for resonances? And in the case of Schrödinger operators in one dimension with potentials of compact support, the answer is yes, and you get the same Weyl formula with the same leading coefficient as you would expect. So I now have to do a detour. Forget about graphs entirely. The way that I'm going to approach this is by showing that the resonances coincide with the zeros of a certain entire function. And this entire function is a function of the type which I've written down up here. It's a sum of complex exponentials with certain real numbers sigma in the exponentials, which you can put in strictly increasing order. And so there are two problems here, and this caused one of the greatest difficulties in the original paper that I had with Pushnitsky. The first thing is to identify what the analytic function is and to count the zeros of this analytic function. That is, the zeros whose modulus is less than or equal to some large r. And the second is to actually deal with the question of multiplicities. Because when you're talking about the multiplicity of resonances themselves, you're talking about the number of eigenvectors associated with any particular resonance. So you have to decide whether you're thinking about algebraic multiplicity or geometric multiplicity. Whereas when you're talking about entire functions, you're talking about the order of the zero. It might be a simple zero, it might be a multiple zero. And so the issue is to prove that these two multiplicities, the order of the zero of the entire function and the algebraic multiplicity of the resonance, actually coincide. Yeah.
You have a Z-independent constant.
A Z-dependent constant.
Independent. Well, just a constant. Because
Well, you could have. I mean, I'm not saying that these
you
sigmas
don't
are
say that
non-zero.
sigma 1 is not bound, is not okay, sigma 1 can be 0.
In fact, in the application, sigma 1 is negative and sigma n is positive. And for the Weyl law, as it happens, sigma n is the volume of the finite part of the graph, and sigma 1 is minus the volume of the finite part of the graph. And yeah, there certainly could be zero sigmas. Absolutely. So one needs, when one goes through the calculations, and I'll show you how this is done, one needs to know something about the asymptotics of the zeros of entire functions of that type. Unfortunately, there's a theorem of Langer from about 1931, which summarized quite a bit of earlier work and said the following, that first of all, the zeros of such an analytic function, entire function all lie in a horizontal strip of finite width, and that secondly, if you want to know the number of zeros which are within a distance r of the origin, then it's given by this asymptotic formula, in which the effective volume, although of course he wasn't thinking in these terms, or the effective constant is sigma n minus sigma 1, the largest value of sigma minus the smallest value of sigma. And so our task is first of all to show that this type of analytic function is the one which is to which the resonance problem can be reduced, and secondly to actually evaluate sigma n and sigma 1 in this particular case. Now, in the later work with Exner and Lipovsky, the problem with other boundary conditions becomes a little more complicated because instead of having a function of this type, the constants a sub r have to be replaced by polynomials. But there is a similar theorem for polynomials, except that you no longer can say that all the zeros in the entire function lie in a finite width horizontal strip. They then lie between two logarithmic bounds as the real part of the variable increases. But anyway, here's the picture with all the resonances lying in a horizontal strip. I've shown the strip as being below the real axis because in our application it is, but in more other cases, if you just look at the general theorem, they're just two horizontal strips. Okay, so let's get back to the graph theory problem. How are we going to do it? What in fact do we have to solve? First of all, I want to point out a certain identity. We're going to be using n, supposing there are n finite edges, m leads, and v vertices, and each vertex has ri edges or leads attached to it. Then we have this identity. Now, there are several ways of looking at this identity, but if you think of it geometrically, each finite edge has two ends, whereas each lead has only one end. So the total number of free ends is twice the number of edges plus the number of leads, which is 2n plus m on the right-hand side. Now you can count free ends in another way. That is, you can go through each vertex one at a time and say how many ends are attached to that vertex. And if you do that, you get the right-hand side. Now, so that's one way of looking at things. Yeah, you can also ask about how many variables you need to control. Well, we're trying to solve minus f double dash equals k squared f. That's a second order ordinary differential equation. It has two linearly independent solutions, and they are of this type, which has two free variables, alpha I and beta I. So the finite edge has two free variables which you need to determine. The lead, on the other hand, since we're defining resonances by being of that form, there's only one free variable to determine the function on the lead. So the total number of variables, the alpha i's and beta i's for each finite edge, and the gamma i's for each lead, is again 2n plus m. Now, what about the number of constraints? So we're really just saying we now need, since we know that the resonance is going to be of this type, it's got 2n plus m free variables, and they have to satisfy the constraints at each vertex. Now, how many constraints are there? It's of course going to turn out to be exactly the same number. Namely, you've got a continuity condition at a vertex. Now there are Ri free edges, Ri edges coming together in that vertex, and all the functions have to have the same value as you approach that vertex. And that gives Ri minus 1 conditions, because you can specify the value of the function on one of the edges at a vertex, and then say all the others have to be equal to it. And then the final condition on the sum of the derivatives gives you the final continuity boundary condition, and so the number of constraints associated with each vertex is actually R sub I. When you add these, you get the right-hand side. So you have linear constraints on 2n plus m linear variables. And now let me have a look at what the actual constraints look like. The functions involved on the edges are all of the form alpha I e to the ikx plus beta I e to the minus ikx. We have to evaluate this at the two ends of the edge. We also have to evaluate the first derivative at the two ends of the edge. Now, if you evaluate this at the end, at one end, you just get a constant which doesn't depend on k, and at the other end, you get an alpha I e to the I k times the length of the edge, ci, or e to the minus I k ci. So when you differentiate, it's the same thing. So everything that is involved in the constraint is either a constant or a multiple of e to the I k ci or of e to the minus I k ci. As far as the leads are concerned, when you evaluate this at the end, the only end is x equals 0, you just get a constant. If you evaluate the derivative, you get a constant. So all of the constraints are linear in the alphas, betas, and gammas, and they may or may not involve e to the I k ci or e to the minus I k ci, where ci are the lengths of the finite edges. So of course, we're trying to solve a linear problem with 2n plus m variables and 2n plus m constraints. So we're really eventually just trying to find whether the relevant determinant is 0 or not. If the determinant is 0, then you have a resonance, and if it's non-zero, you don't. Now, I'm going to calculate the value of the determinant in the crudest way possible. That is, you multiply one element from each row and each column, and you multiply them. After multiplying them together, you add over all possible permutations. But the point is that the individual entries of this rather large matrix are all involve either constants or e to the plus or minus I k c sub I. I apologize for the fact that I'm using I for two different things, and I will leave you to work out which I is which. It shouldn't be too demanding. So in the end, when you sum over all possible products of the entries, you do in fact get an expression of the type which I showed you before, the middle equation for f of k, and the sigmas are combinations of either CJs or minus CJs or possibly just zeros. So you have all in principle you have all possible sums of CIs, minus CIs, or just they're absent. The largest possible sigma that you could get would be that every CJ occurred with a positive sign, and then you'd be looking at the sigma, which is the sum of the CIs, and that is of course the length of the finite part of the graph. And the smallest possible sigma that you could get is where all of the CIs do occur, but they all occur with negative signs, and in that case you get minus the volume of the graph. And so the difference between the largest and the smallest sigma would be twice the volume of the graph, and there's the number 2 turning up, and so you end up with what you want. We appear to be finished. Now, if that was all there was to the subject, it would not be terribly exciting, because I would be saying, look, this is the obvious conjecture. Eigenvalues turn into resonances when you add on these infinite leads. Yes?
Sorry, you say that they turn into resonances. Is there a one-to-one correspondence?
The zeros and the resonances are in 1-1 correspondence.
No, the eigenvalues and the resonances when you add the leads. Can you establish one-to-one correspondence?
Well, we'll get to that in a moment. Okay. Yes. I mean, there are certain things which are just reasonable expectations.
No,
yes.
I mean,
and obviously that is
that
is an obvious issue. Yes. And it's not going to be as simple as it appears to be. So the answer is we are not finished. And there's a very obvious reason why we're not finished. Because when I told you the earlier theorem, Langer's theorem, for the asymptotics of the zeros of a function of this type, and it said it depended upon the difference between the largest sigma and the smallest sigma, that assumes that the coefficient a sub r associated with the smallest and the largest coefficient are non-zero. And I haven't given any reason to believe that when I said the largest possible sigma is this, and that the smallest possible sigma is that these actually do turn up when you expand the determinant. And so this becomes the problem. You have this rather large and unstructured matrix, which is 2n plus n times 2n plus n. You know that the determinant is of this general form. You know what the asymptotics of the zeros are going to be, but it depends upon the largest sigma and the smallest sigma, the difference between them, provided the coefficients of that largest and smallest sigma are actually non-zero. And so one has to actually devise a method of working out whether this is the case. And fortunately, I say fortunately because it's always better to have a surprise than just have your expectations confirmed. The answer is that this is not always true. The Weyl law for resonances sometimes does not hold, and therefore there can't be a 1-1 correspondence between the eigenvalues and the resonances. And indeed, the result holds if and only if every external vertex is unbalanced. Now, probably the easiest way to explain what that is to go back to the picture here. You look at two different types of vertices. I would call that an internal vertex, and all the others in this particular case are external vertices. The external vertices are those which have at least one lead attached to them. So if you take a typical case like this, you have one lead and two edges attached to it. And since 1 is not equal to 2, I call that vertex unbalanced. And if you look up to, let us say this one, there's 2 leads and 3 edges, so it's still unbalanced. but of course I drew this one in where you have 3 leads and 3 edges at it, so that is a balanced vertex, and because there is a balanced vertex, this graph does not satisfy the Weyl law for resonances. So it's not just that the result is not true, in which case you say, well, that wasn't a very good problem. It's a pity, but it's not a very good problem. But there is actually a simple geometric criterion which enables you to determine whether the thing is true or not without doing any of the calculations. Just look at the graph. If you have at least one balanced vertex, then the Weyl law fails. Now, one of the possible explanations for this, I mean, it's wrong, but it's a possible explanation, is that you think of these quantum mechanical particles moving around the graph, and every time they come to a vertex having to decide which way to go, and that if you have a unbalanced vertex, then when it comes along here, it's got a quandary because it's sort of easier to go back in than to go out because there are more edges attached to it than there are leads. But that at this point, since it can come in from 3 ways and go out from 2 ways, then in some way this vertex is less visible to the particle than one of the other vertices. You could argue that perhaps you could alter that vertex so that this lead just continues on to that one, this edge continues onto that one, and this edge continues onto that one, and so you can replace that vertex by a non-vertex with each of the edges each of these edges becoming amalgamated with one of the leads. And so you might argue that that's the explanation of it, and that really the effective volume is obtained by deleting that vertex, and then you would also have to delete these 3 edges because they would now become part of the lead. And so you say, well, then probably in this case the effective volume is the volume of the part of the graph which does not include those 3 edges, and that's wrong. And in fact, it is following a number of examples, it seems very hard to give any effective formula for saying what the effective volume is. The effective volume, of course, exists because Langer's theorem tells you that the asymptotics of the zeros of this entire function f is given by the difference between the largest and the smallest sigma. The largest and the smallest sigma being required to have non-zero coefficients. If the leading coefficient vanishes, then you just eliminate that term from the finite series defining the function f. Okay, so now the situation is in this particular case is fairly easy to understand. If you now go on to look at other boundary conditions, not just the Kirchhoff or free boundary conditions, but other ones, then you find that the situation changes and it becomes really quite complex. If you can do one other thing as well, you could actually say that on each of the edges of this graph, rather than having the operator minus d squared by dx squared, you could have a constant times minus d squared by dx squared. So as well as having a variable length for each edge, you could also have a constant coefficient operator times minus d squared by dx squared, but keep the free boundary conditions at the vertices. That gives you yet another formula, which I'm afraid my time prevents me from telling you, but it is not just simply equivalent to the problem which I've told you, because you might think that you could just reduce it to the other problem by doing a suitable scaling of the lengths of the edges in order to remove the constant in front of the d squared by dx squared to 1 and change the length of the edges. Now if you do that, which you can, then you can reduce it to this sort of problem, but now the boundary conditions at the vertices change as well. And so as I was referring to this paper with Exner and Lipovsky, which gives a very systematic treatment of this problem for a wide range of different possible boundary conditions. Anyway, this is the result. Can I actually explain to you? It's still a little time. Can I explain to you the strategy of the proof? Well, I won't give you the actual proof because it's not very illuminating in some ways. But the strategy of the proof is as follows. Well, it starts off without any of the leads. So you just have a finite graph with finite length edges. Now in that case, the Weyl law is known to be true. There are no resonances, or in my language, all the resonances are actually eigenvalues. The spectrum is discrete. The asymptotics of the eigenvalues can be determined by a straightforward change of the boundary conditions. If you have a graph without leads, then you can change the boundary conditions to either Dirichlet or Neumann for each edge and decompose it as a sum of a finite number of disjoint intervals for which the asymptotics can be calculated, and then by Neumann-Dirichlet bracketing you get the same answer. Okay, so for finite graphs the leading term of the spectral asymptotics is well understood. Now what I want to do is build up by an inductive process from the finite graph to the full graph that I've shown here by dealing with each vertex one at a time. So start off with a graph with no leads and then choose arbitrarily one of the external vertices and then just add the two leads associated with that vertex in. Now what you've done when you add these two leads in but none of the others is you've brought in two extra variables, the gamma I e to the I kx on each of the two leads. So the matrix has become slightly bigger, and it would be nice to say that you could just write the new matrix as a block matrix in which the original block appeared in the bottom right hand corner, and then this 2 by 2 thing occurred in the top left hand corner, and the determinant of the product was just the product of the determinants of the two parts. But it's not quite so simple because when you add in these two edges, the Kirchhoff boundary condition at this point changes. The Kirchhoff boundary condition at this point requires you to add up the sum of the outgoing derivatives on the finite edges. But now you have a different Kirchhoff boundary condition because you have the two leads and you have to add those up as well. So you don't just add up, you add in two variables, but you also have sort of a linking with the variables which are associated with these three edges. So the new matrix is the determinant of the new matrix is not simply a product of the determinant of the old matrix times some 2 by 2 bit determinant. However, that's not really what you need, because all that we're actually interested in is the coefficient of the leading term. The question of whether the term with the smallest value of sigma or the term with the largest value of sigma have non-zero coefficients. And what you can actually do when you examine this matrix rather carefully is you can work out the relationship, a precise relationship between the coefficients of the largest and the smallest sigma in terms of the coefficients of the previous finite graph. And what you do when you do this calculation is you discover that the smallest coefficient, sigma 1, always has the right non-zero value, whereas for the largest coefficient, when you calculate what it becomes when you add on these two extra leads, it depends upon whether the number of leads you add on is equal or not equal to the number of edges you had previously. So you go around these vertices, the external vertices one at a time, and at each stage you check whether the first and the largest and the smallest value of sigma have non-zero coefficients. It turns out that the smallest sigma always has a non-zero coefficient, and as you go around with the unbalanced vertices, the largest sigma remains having a non-zero coefficient unless you come at some point to a balanced vertex, at which stage that coefficient turns to 0, and at all remaining stages it remains 0. So that's really roughly the strategy. If you want to see the calculations, then you can go to the archive and read them. Now, I've got about 10 minutes left, perhaps a little less, and I want to give you a feeling for what's really happening here. because it is rather puzzling. I'm going to look at this particular graph. Forget the dotted lines for the moment. We've got two leads coming out like this, going off to infinity, and two finite edges, which I have chosen to represent as parts of a circle. The total length of the circle is 2 pi. The number c, well, if you replace c by minus c, all you're doing is interchanging the top circular edge by the bottom circular edge. So there's a symmetry between c and minus c. I only need really to worry about the case where c lies between 0 and 1. The vertices here are unbalanced. There are two finite edges and one lead at each of the vertices, and so the Weyl law should be true in this case. Except, unfortunately, in the case where c equals 1. As c gets closer and closer to 1, the top curved edge contracts to a point, and eventually the situation is that you have a single finite edge with two ends both coming together at one vertex and two leads going out of that vertex, so it's balanced. Now, if you feel a little uneasy about having a single finite edge which has two of its ends at the same point, then you can perhaps feel more reassured if you like to put 5 points around here at any positions you like. You can turn that single curved edge into 5 edges, and then you get away from the emotional problem of having an edge which starts and ends at the same point. Okay, so now what size matrix are we talking about in this case? Each of the two finite edges has two variables, alpha, beta, and each of the infinite leads has one variable called gamma. So it's 2 plus 2 plus 1 plus 1, and we're talking about a 6 by 6 matrix. So one could simply write down with a little struggle what the determinant of that 6 by 6 matrix is. And this is where the dotted lines come in, because if you look at this dotted line, you can see that the graph is symmetrical with respect to reflection from left to right. And so the problem can be decomposed into two independent problems, one of which is even with respect to left-right reflection and the other of which is odd. And what that means is that if you choose to take suitable basis for the 6 by 6 matrix, it decomposes as a product of a block product of two 3 by 3 matrices, and so that makes the calculation easier. Now, if you like to do it not by changing basis for the matrix, you can do it more geometrically. If you, for the odd problem, you look at functions which are odd with respect to the reflection, and that means they vanish at the top and bottom of the circle, and so you look at the problem for the half graph with Dirichlet boundary conditions at the two free ends. Whereas if you look at the even problem, then the functions will be even, and you look at the problem for the half graph with Neumann boundary conditions at the two free ends. And the end result, whichever way you do it, is that the determinant of this 6 by 6 matrix can be written as the product of two functions, and the functions are in fact precisely these. So those functions are in fact the determinant of the 3 by 3 submatrices. Now, if you look at these, they are in fact of exactly the right type. I said that the functions we're looking at should be a sum of complex exponentials. There are actually sines and causes here, but of course causes and sines can be written as the sum or difference of two complex exponentials. So these functions are exactly the same, the right character, and you can look at the asymptotics of the zeros by using Langer's theorem, but you can also do it numerically. I mean, notice that if even in this case, you can't actually solve it in closed form. I mean, finding the zeros of a sum of two causes and a sine is not a finitely explicitly soluble problem. It's a numerically simple problem, and I'm going to show you what the solution is. So what we expect is that, and what we know, in fact, if you believe the theorem, is that if c is not equal to 1 or minus 1, then the asymptotics of the zeros of this should be exactly what the Weyl law expresses, and the volume here is 2 pi. Whereas if C equals 1, then something strange should be happening. And so here are the numerical results. Now, this is a resonance. Well, you say it can't be a resonance because a resonance is a point, and I seem to have shown some rather complex curve. This is the curve that you get from a resonance by letting C vary from 0 to 1. For any particular value of C, you have 1 point on this curve. Now, I'm describing it as being a single curve, but there's no pointer, is there? No.
Yeah, here.
Oh, yes. Okay, so notice first of all that here is a point on the real axis at the number 7, and that corresponds for certain values of C being eigenvalues. So eigenvalues are included as special resonances. The actual situation is you start with C equals 0 there, and then it turns into an eigenvalue at C equals 1/7, then it comes down the next loop, and it goes back to being an eigenvalue at 3/7, and then it goes back to being an eigenvalue at 5/7, and it goes back to being an eigenvalue at C equals 1. I had said, of course, that you can have embedded eigenvalues when you have a closed loop where the lengths of the edges are mutually rational. Now, in this case, the lengths of the edges are 1 plus or minus C times pi, and the ratio of those is rational if and only if C is rational. So you get an embedded eigenvalue for this associated with this particular one when C is 1/7, 3/7, 5/7, or 1. Now, as you choose larger and larger values of this integer, what you discover is that the number of loops you get increases steadily. But for each particular value of C, there is exactly one resonance inside this rectangle. I can prove rigorously that there is never a resonance going through a half integer, 6.5 or 7.5 in this case. They're enclosed between 6.5 and 7.5. And also, we can prove that there is no resonance which crosses a negative imaginary horizontal line. Well, we already proved that from Langer's theorem. So this is what happens. And there is nothing apparently going wrong. There is a 1-1 correspondence between the integer 7 and the resonances which lie inside those boxes, and they all vary continuously with C, and as C goes to 1, they just converge back to that, and so there is nothing apparently happening. For all values of C, including C equals 1, the Weyl law says that the number of resonances is exactly the same as the number of eigenvalues. So the problem all arises in the even situation, and here it is. Now I've taken a different integer here, 4, and this again is a plot of how the resonance behaves as a function of C. It starts off there as C equals 0, and then it becomes an eigenvalue at C equals 1/4, and then it becomes an eigenvalue again at C equals 3/4, and then as C gets closer and closer to 1, this eigenvalue starts drifting off to infinity. And if you look at the even resonances, every resonance goes off to infinity and hits infinity exactly when C equals 1. So half of the resonances disappear at C equals 1, and for all other values of C, you get the Weyl law. Again, there's the theorem which says that no resonance can go through either a half integer, 3.5 or 4.5. So the resonances can't go from one eigenvalue to another. They can only go back to the eigenvalues they started with. For the unbalanced case, there always is a resonance, and there's exactly one resonance in the appropriate place. For the balanced case, you can have a situation in which half of the eigenvalues, or some fraction of the eigenvalues, all simultaneously vanish. The situation is actually, even for this particular example, is very complex. That is actually the final slide. When you do some other simple examples, you find in some ways the same sort of thing, but the fraction of the resonances which disappear off to infinity when it becomes balanced seems to be a global property of the entire graph. In other words, if you ask what is the first non-zero coefficient in the entire function which Langer dealt with, it's by no means obvious, just by looking at anything from the geometry of the graph, what the answer should be. So we don't have a good general formula which says what the effective volume is for all graphs. All we have is a good general geometric rule which says the Weyl law holds if and only if there is no unbalanced external vertex. So there's obviously plenty more to be done if anyone wants to do it. Quite apart from this, you could now imagine, if you want, other generalizations. For example, you can have a Schrödinger operator on each edge rather than just a constant multiple of d squared by dx squared. We haven't even attempted to think about this one, but it clearly could be interesting. Okay, thank you.
So, are there questions, comments? Yeah.
It's first about 10 years ago, I read a paper by Kotos and Smilansky, studied scattering. Kotos and Smilansky,
Right.
quantum scattering and resonance on graphs or something like this, who basically studied very similar problem and also derived Weyl asymptotics. Can you comment on the similarities and differences?
Well, I certainly can't. It is, in fact, very common that people assume, without saying it, that they only attach one lead to every vertex. So they take a graph and then they attach a lead in certain places. So the thing which provides a novelty here, quite likely, is that we allow an arbitrary number of leads to be attached to every external vertex. And in fact, we were for some time very confused, because when you attach a single lead to every external vertex, then you do get the Weyl law, assuming you don't attach it to a free end. And so it's only when you look at this more general problem that you have any possibility of getting into trouble. And the reason that we got into confusion was because when we were looking at more general things, we started off by looking at only one lead coming out of each vertex. But then we also looked at this final example, and clearly, in this final example, which works perfectly well for c less than 1, it fails for c equals 1. And trying to understand what was going on eventually made us realize that the question of the number of leads which comes out of a vertex was absolutely crucial. Now, I don't know the paper, maybe you know it. No. So you'll have to try and find out more about it.
Second question is also maybe a suggestion. As you mentioned, the whole problem arises from the specific boundary matching conditions that you take the vertex. So this goes back to this correspondence between eigenvalues and resonances. So maybe by varying the coupling between the lead and the graph, you can actually see how the eigenvalues move from real axis into
Yes.
and then when the coupling gets strong enough to Kirchhoff, then you'll see an escape.
That's absolutely right. And there are several different ways of doing this.
Okay.
But basically what happens is if you have generic couplings at vertices, then the Weyl law generically holds. But there will be certain special values. You have continuous parameters now. You have certain special values, a manifold of special values, at which the Weyl law fails. What is happening in this particular case is that you don't see it as being a variation of a continuous quantity. You see it as being a discrete issue. But if instead of doing this, you can have a graph with balanced vertices, for which the Weyl law is true, if you take other than Kirchhoff boundary conditions, and then you can see as the boundary conditions converge to the Kirchhoff ones, some of the resonances go off to infinity. That's absolutely correct. Yes.
Other questions, comments?
Since my name was mentioned,
Sure.
the way that Kotos and I were counting the resonances was by using the total phase of the scattering matrix, so the phase of the determinant, which is connected to the Klein formula and such things. And there, the resulting counting of resonances also would come from a certain determinant which is independent on the number of leads that you are connecting to the number of leads that you are connected per vertex. So maybe one of these things is the reason for the fact that it doesn't appear in our computations. And maybe after you read the papers, we can discuss it.
Yes. I very much like to. Thank you.
Okay, that was Uzi's comment. Other questions, comments? If there are none, let's thank Brian again.